Hi everyone! In this video we're going to go over another electrophilic aromatic substitution reaction called the Friedel-Crafts alkylation reaction. We'll also go over Friedel-Crafts acylation and then Clemmensen reduction. Alright, so Friedel-Crafts alkylation was discovered by Charles Friedel and James Crafts in 1877. And in this reaction, you can add an alkyl group to your benzene ring. So similar to all our other reactions we've looked at so far, we start with benzene, which is a weak nucleophile, and we're going to use an alkyl halide. So the R group is an alkyl group. And we're also going to use that aluminum trichloride catalyst. And this is just going to add the R group to your benzene ring. So the R group can be a methyl group, an ethyl group, and that could go on. You could do propyl, butyl, etc. You could also add a branched alkyl group. So for instance, isopropyl or tert-butyl. The main thing here is notice we don't have any double bonds or triple bonds on our group. So these have to be alkanes, so all single bonds. All right, so let's look at the mechanism for Friedel-Crafts alkylation. So let's say we're trying to add a tert-butyl group to our benzene ring. So we'll start with our alkyl halide, and again, we're using that aluminum trichloride catalyst. Oh, aluminum, there we go. And remember, aluminum trichloride has an empty p orbital that acts as a Lewis acid, so it can accept electrons from our chlorine. So once we've formed our adduct, aluminum becomes negatively charged, chlorine becomes positively charged, and what's naturally going to happen is the shared electrons between chlorine and our carbon group, our alkyl group, those electrons are going to move over to chlorine. And we end up forming a carbocation plus aluminum tetrachloride, and aluminum is still negatively charged. So this is a tertiary carbocation, which is very stable, but make sure to watch out for rearrangement because, for instance, if you form a secondary carbocation, but there's the opportunity to have a tertiary carbocation, then you might end up with a 1,2 methyl shift or a 1,2 hydride shift. So just make sure to watch out for rearrangements. When rearrangements can occur, you often end up with a mixture of products. So we'll go over that later. But here we have a perfectly stable carbocation, so now we're just going to add benzene into our reaction. And the carbocation is a really strong electrophile, so benzene can now attack that electrophile, and we end up with our intermediate, the sigma complex, or a rhenium ion. All right, so now we need a base that can take that proton at the top so we can reestablish aromaticity. So we can use aluminum tetrachloride as our base. And actually, I'm going to draw this aluminum tetrachloride slightly differently just to show what's going on here. So the chlorine, that extra chlorine, is going to grab onto that proton. We'll leave the shared electrons behind to reform our benzene ring. And we get our final product, which has a tert-butyl group on the benzene ring. So this is called tert-butyl benzene. Now, we've also reformed our catalyst, and we also formed some hydrochloric acid. All right, so let's do some practice problems. So I'm going to draw a benzene ring and give you some reagents for two different problems. And then I want you to try to figure out what the product or products might be. So in the first problem, we have a 3-carbon chain in our alkyl halide. In the second problem, we have a 2-carbon chain in the alkyl halide. So we have a propyl group and an ethyl group. All right, and then we'll just draw a big old box where the product or products should go. So I want you to pause the video, try this problem, or both of these problems on your own first, and then when you're done, we'll go over them together. All right, so let's start with the first problem. So again, we have a 3-carbon chain on our alkyl halide. Now, when we form that carbocation intermediate, what type of carbocation would we have? Would it be primary, secondary, or tertiary? Primary, right? Because the chlorine is going to bond to aluminum, and then the shared electrons between chlorine and the carbon group will shift over to chlorine. So initially, we end up with a primary carbocation. But is there a more stable carbocation? Can we go through some sort of rearrangement here? Yes, we could have a 1,2 hydride shift. To give us a secondary carbocation. So this is actually going to give us two products. And we'll end up with a major product, which is more stable, and a minor product, which will be less stable. And this also sort of has to do with kinetics and thermodynamics as well. So in the first product, we're just going to see benzene bonded to that initial propyl group. So again, we want to count our carbons, 1, 2, 3, perfect. But we could also form a second product with that more stable carbocation, which is an isopropyl group. All right. So which one do you think is the major product? The isopropyl group bonded to benzene, that will be our major product. And that's just because it is a more stable, it has a more stable carbocation intermediate. And so that will be the major product. But the other product, the minor product, does form as well. And in fact, if we did this experiment, we would find that about 65% of our product will be the major product, and about 35% of our final product will be the minor product. So we'd have a mixture of these two. But remember that if you have constitutional isomers, which is what these are, you can typically separate them based on boiling point or other physical properties. Okay, so let's look at the second problem. Here we have a 2-carbon chain on our alkyl halide, so we have an ethyl group. And what type of carbocation do we expect to form? A primary carbocation. And is there any way to create a more stable carbocation? Nope. Even if we shifted a hydrogen over, we'd still have a primary carbocation, right? It would just be on the other carbon, so they're the same. Okay, so that means we only have one product for this problem. So we'll end up with a benzene ring bonded to an ethyl group. And again, always remember to count your carbons because it's very easy to lose a carbon or gain a carbon when you're drawing these molecules. So always go back and just double check that you have the right number of carbons. All right, so let's talk about some limitations to the Friedel-Crafts alkylation reaction. So the first limitation, actually I'm going to switch my marker color here. So the first limitation is, again, primary alkyl halides can rearrange, just like we saw in those practice problems. Now, if you have a methyl carbocation or an ethyl carbocation, those are exceptions. You can't rearrange them to get a more stable carbocation. So we'll just write plus CH3 and plus CH2CH3 are exceptions. All right, now the second limitation is only sp3 hybridized alkyl halides work for this reaction. So what that means is only alkyl groups that have all single bonds, so only alkanes work. So you can't have a double bond or a triple bond in your alkyl group. The next limitation is alkyl groups are electron donating groups, so they're considered activating. So that just means that if you have, let's say, tert-butyl that you're trying to add to your benzene ring, often what happens is you end up adding too many alkyl groups. So let's just write that down. So alkyl groups are electron donating groups, or activating groups. And we'll talk more about activating groups later on. But really what this means is that you're going to see over-alkylation. So when you add an alkyl group to your benzene ring, it activates the ring and it wants to keep reacting. And so you could add multiple alkyl groups. So for example, let's say we did the reaction we saw earlier where we have a tert-butyl group that we're adding to our benzene ring. Often we have excess reagents lying around, right? So there's excess molecules of our alkyl halide in the reaction mixture. And again, because the tert-butyl group is what we call activating, this is going to cause the ring to want to react again. So then we end up with, oh, actually let me give myself a little more room with this product. So we actually end up forming a molecule that has two tert-butyl groups on the ring. Okay, and then the last limitation is that if you have, let's say, an electron withdrawing group instead of an electron donating group on your ring already, that might cause the ring to be unreactive. So another way of saying that is strongly deactivated aromatic rings cannot perform the Friedel-Crafts alkylation. And we'll talk again more about activating and deactivating groups and what that means later on, but it's just good to know these limitations going forward, and we'll come back to them later. All right, so now there is another type of Friedel-Crafts reaction called a Friedel-Crafts acylation instead of alkylation. So an acyl group is one where you have a carbonyl group bonded to some sort of alkyl group. So just as an example, let's say we start with benzene as usual. And let's say we add this molecule in here. So we have some sort of carbonyl or ketone there bonded to chlorine. And again, we're going to use aluminum trichloride as our catalyst. This is going to add that acyl group to the benzene ring. So the mechanism for this is very, very similar to the one we saw before, but let's just go over it because there are some slight differences. All right, so let's start with our acyl group here bonded to chlorine. And again, we're going to see a reaction with aluminum trichloride because it's a good Lewis acid. So chlorine will donate its electrons into that empty p orbital on aluminum. And we form that same adduct that we've seen before, where aluminum is negatively charged and chlorine is positively charged. So similar to the alkylation mechanism, the shared electrons between chlorine and that carbonyl group is going to move over to chlorine. And we're going to form, let's see, we've got our positively charged acyl group plus our aluminum tetrachloride molecule. Now, there is a resonance structure here for our acyl group. So the lone pair on oxygen can move down to alleviate that positive charge on the carbon below. And that will form a triple bond between carbon and oxygen is positively charged. And this is what creates our electrophile that the benzene ring can react with. So let's add in our benzene ring and show that reaction here. So benzene's going to come in, attack that central carbon, which will move pi electrons back over to oxygen. And we get our sigma complex, or rhenium ion. All right, so now we need something to take that proton at the top so we can reestablish the aromatic ring. So again, we're going to use our aluminum tetrachloride molecule. And the chlorine is going to grab that hydrogen. We'll leave electrons behind. And we get our final product. And remember that our group could be anything. It could be methyl, ethyl, propyl, etc. So you could add any sort of acyl group there to the ring. Now we're also going to reform our catalyst and a little bit of hydrochloric acid. Okay, so what if we wanted to turn that into just an alkyl group? So what if we wanted to reduce the carbonyl group? Well, we could perform what's called the Clemmensen reduction. And the Clemmensen reduction is really advantageous in situations where you do end up with multiple products. So, like we saw earlier with our practice problem, if you have a propyl group in your alkyl halide that you're trying to add to the benzene ring, we saw that you actually end up with a mixture of products. So we form about 65% of the product with the isopropyl group, and then we form about 35% of the product with the propyl group. So what if we just want to form the minor product with the propyl group attached? What if that's our desired product? Well, one way to form just that product is to use the Clemmensen reduction. So this is kind of a little trick that you can use. So what you'll do is first you're going to add an acyl group that has 3 carbons. So let's just highlight those carbons, 1, 2, 3. All right, so we know that that is going to attach itself to the benzene ring. Still got those 3 carbons there. And then we're going to add a zinc mercury amalgam, so a mixture, and hydrochloric acid. And this is going to reduce the carbonyl group into just a simple alkane. All right, and that's our desired product. And then we don't have a mixture of products like we saw in the previous reaction. Okay, so the pros and cons here for this reaction. So the Clemmensen reduction. The pro is that you can make a specific product without a mixture of products. But the con of this reaction is if your substituent, the functional group that you're adding, if that is acid sensitive, mercury has to be used, and mercury, again, can be toxic and dangerous to us. So we can't use if substituent is acid sensitive. All right. So again, this is really useful if you're trying to avoid rearrangement of your carbocation intermediate, because in this case, you have an acyl group instead that's bonding first, and then you just reduce this using your zinc-mercury mixture with hydrochloric acid. Okay, so we'll stop there, and next time, so probably next week, we'll talk about activators and deactivators. So earlier when I talked about a group being activating or deactivating, we'll go into more detail about that. And then we'll also talk about electron withdrawing groups and electron donating groups as well. So I will see you then.